Well, good morning from Toronto, Canada, and welcome to our final webinar for this year. My name is Armin Mulkey, and I'll be your host and moderator for today. Today's presentation will be given by my colleague, Mr. Michel Levis. Mitch has been with Quanser for almost 2 decades and is a research and development engineer within our academic applications team. Today, Mitch will be demonstrating how to use a variety of MathWorks toolboxes, including the System Identification and Symbolic Math Toolboxes, to model a Quanser Aerospace system and design a third-order PID controller. Now, I know everyone's eager for us to get started, but before we do, I'd like to go through a few housekeeping items just to let you know how you can participate in today's session. Mitch, the audience is all yours.
Thanks, Armin. Hope everybody's well, and welcome to today's webinar. So, without further ado, let's get started. So I think some of you that have registered may already be familiar with the Quanser AERO. So the Quanser AERO hardware, if you're not, then that's fine. This webinar will be a great introduction to the system as well. So what does the Quanser AERO have? The Quanser AERO is a 2 DOF reconfigurable aerospace system. So you have a number of sensors and actuators, and I'm just going to overview them so you know what is available, because we will be using some of these in this webinar. So to measure, first of all, it has 2 actuators, right? So it has 2 rotors with DC motors mounted on them. There are 4 encoders in total. So there's an encoder on each of the rotors to measure the position of the rotor, but and also the angular rate of the rotor. You also have a encoder on the pitch, which is used to measure, of course, the angle of the pitch, and the yaw as well. So you have a pitch, so you can measure the angle of the yaw using the encoder, and you also have an IMU. So you have a 3 DOF accelerometer and 3 DOF gyroscope on the IMU that is on board. You have 2 different sets of blades for the rotors. There's a slip ring mechanism, so the yaw is allowed to move continuously. And I mentioned that it's reconfigurable, so you can change the angle of the propellers. So you can change the angle of the propellers, and you can also lock the pitch or lock the yaw axis. Note that we also have the virtual twin, right? So we have the QLabs virtual Quanser AERO that is also available. So the analysis I'm conducting in this webinar could all be performed on the virtual twin. So today we're going to be dealing with the 1 DOF pitch-only configuration. So this resembles, here's an aerospace system called the Osprey that resembles those dynamics, right? So you have both rotors parallel to the ground in a horizontal fashion, and you have in the free body diagram is on the right there. So it's only allowed to move along the pitch, and you have a force on each of the thrusters. So what's the problem, right? It seems relatively simple, but there's actually several modeling and control challenges with this experiment. So let's look at them more closely, right? So here we have the 1 DOF system. First of all, you have some actuator limits, right? So you're only allowed positive commands, and you're limited to 24 volts, right? So we can peak at 24 volts, but we can't surpass that. So that's the limit of the amplifier. Next is the rotor dynamics. So given that the rotor is being driven by a DC motor, you have a first order system there. And then the second system is the pitch, right? The pitch is what we want to control. So the objective of this is to control the pitch with a reasonable settling time. And the pitch on its own is a second order system. So what we're proposing and what we're going to be doing in this webinar is designing a cascade control. So in order to mitigate the dynamics of the rotor, we're going to be developing an inner loop, so an inner speed control using a PI controller to regulate the speed of the rotor. And then we're going to design an outer loop, a PID controller, to control the position of the pitch. So the PID controller, the outer loop, will be giving a command to the rotor speed control, and the rotor speed control will compute what voltage is needed to reach that velocity. So that's what we're going to be doing today. So to summarize what's going to be in this webinar, what to expect is it's going to be full modeling and control of the DOF Aerospace system, like I mentioned. But while we're doing this, we're going to be leveraging several MathWorks toolboxes, right? So namely the System Identification Toolbox to find the AERO model. We're going to use the Control Systems Toolbox and the Symbolic Math Toolbox to design the controller. Everything here is done in a nice package with the MATLAB live script, right? So it's all well laid out with that live script. Finally, when we're taking measurements from the actual hardware and implementing the control is done through the Quark real-time control software. So Quanser and MathWorks have been partners for quite some time now. We've been using MATLAB and Simulink for over 30 years, and the Quark real-time control software that we supply is seamlessly integrated within Simulink and MATLAB, right? So you're able to leverage all of those amazing tools that it has. So here's the overview, guys. For the rotor speed control, the first thing we need to do is identify the model, but also validate it. Then we're going to design the speed controller, all done through the live script. We're going to simulate it first in MATLAB, right? So we'll simulate it first to make sure that it matches our specs. Then we're going to go and simulate it and simulate that in Simulink with a more representative model of the rotor. Then we switch gears and we go to the AERO body. So the AERO, so for the AERO pitch motion, we also need to identify and validate that model. And then we will design the PID controller to control the pitch position. Then we'll simulate that in MATLAB, and then we'll simulate that in Simulink. Finally, we will implement this on the hardware. So we are basically doing the entire modeling and control design process, simulation, implementation in this presentation. So let's begin with the modeling. The rotor model is fairly standard. So you have a DC motor, of course. There's the schematic of the system, right? The free body diagram, and you can come up with these equations of motion. Note though, it is a little bit different than a DC motor because you have that drag force constantly acting from the prop, right? So you have that constant friction that is much larger than your typical DC motor. You also have a lot more inertia due to the propeller. But this is, at the end of the day, it's a first order transfer function, but you're looking at a larger time constant than you would your standard DC motor, which is why you need a control for that. Now looking at the pitch model, so the pitch, again, here's a free body diagram. You can model this using this very standard equation of motion, where you have inertia, you have damping, you have stiffness, and the force or the torque being that's being applied along the pitch axis. And then you can find out what the second order transfer function is, right? So it will look basically like that. However, the inertia you could find out numerically, but it might not be that accurate, right? So you don't really know the inertia. The damping needs to be identified. The stiffness you can find from the physical parameters. The thrust is unknown as well, right? So the thrust would need to be identified as well. So you got three variables there that ideally you want to find out experimentally. So looking at this is that entire model, you're applying a voltage, you have that saturation limit because of the amplifier. Then you have the rotor dynamics, and that, depending on the motor speed, that will create a certain thrust, a certain force or torque about the pitch, and you'll get a resulting pitch angle. So that's the complete system in series. All right, so let's begin with the system identification procedure. So we are using the Hill-Write and Hill-Read Quark blocks. So these are blocks that are available from the Quark Targets library when you install that software. And that's how we're measuring the response from the AERO. So we're measuring the pitch and we're measuring the rotor using those blocks. And what we're going to do is apply a step at 24 volts for 20 seconds. And then we set that to 0 and we let that go in free oscillation for 20 seconds. So here is a system in action. So I'm running Quark right now through Simulink. And you can see now I'm applying that step. So I'm obtaining a step response of the one DOF AERO, and you can see that it's second order. So the first scope is your voltage, the middle scope is the speed of the rotor, and then the last scope is the pitch angle. Right now, this is in free oscillation, right? So free oscillation, we have 0 voltage, and we're just letting it settle, and we can use that for our measurement as well. The Simulink scopes are logging the data. So we're logging all this data inside the MATLAB workspace, and with those variables, you can plot it in a MATLAB figure. So just another great feature that that Simulink has and that Quark can leverage. And you can also save those variables in an MET MATLAB data file if you want to do offline analysis. So as you can see, the pitch is second order and the rotor is first order. So we can use this data now to identify our model. And we're going to do this using this particular function from the Symbolic Math Toolbox called TF estimate, right? So we're estimating a transfer function. So what I'm doing here, I'm packaging the data using the ID data, the input output data. I give the sampling rate that we used in the model, which was 500 Hertz. And I'm setting the options to 0 initial conditions. And I say, okay, identify the first order rotor model. And then we compare. So the compare command is another very handy function that the System ID Toolbox allows us, where we can compare the model with the measured data. So when we run the compare command, you can see that the model matches very well, right? We're at 99.6 accuracy rate. So quite good. And there's the model that was identified. So we have a time constant of about 0.05, which is fairly large, right? So we're done with the rotor. That was it, basically, just a couple of commands. Now we do the same treatment on the pitch. So again, we use the TF estimation, and that finds us a second order. But this time, note that I'm using the different parameters in the function, right? I specify 2 because I know it's a second order function. If we run the compare command, again, it's the model that it generated is very accurate, right? We're looking at 92.1% there. So that's great, right? The model matches the hardware. So that's about it, guys. System ID. So the takeaways are basically we use Quark, showed you how to read measurements and apply voltage using the Quark software. And as you can see, you're using this all through Simulink. And you can really quickly estimate and validate models using the System Identification Toolbox, right? So using the TF estimation and compare commands. Now, I'm just using a handful of functions from System ID. It's a huge toolbox. It's been around for a long time and for good reason, right? You've just seen the power of it. But you can use it to identify different models like nonlinear models, arcs, as well as state space. And in fact, we published a blog last week on how to identify the state space model of our rotary flexible link. So if you're interested in that, please go ahead and check that out. And we also show you how to design an LQR controller. All right, so now we move on to the control design, simulation, and implementation portion. So let's start with the inner control, right? So this is the inner control that will regulate the speed of the rotor. So we're going to be designing a PI controller. Now, this is not your standard like PI controller, right? What we're doing here is we're feeding back the process variable, which is the rotor speed, the proportional term directly in the input, right? Not given the error. So we're feeding this back directly. Now we're doing that for a reason, because we want the closed loop transfer function of the rotor to match our second order prototype function. And we're doing that because we're going to do the classic second order design. So based on, and I'm sure many of you are very familiar with this, you have an overshoot and a peak time spec, right? So we want to have overshoot of less than 2.5% and a peak time of 0.15 seconds. So that's the ideal. Those are the control design specifications. They are not really what the expected behavior will be. So the expected or desired response, I in a real system, I want at least, I don't want to exceed 5%, and I want a peak time of no more than 0.2 seconds. Ideally, that's what I'm looking for, right? So there's a difference here, because the control design specifications is what we're using in our control design, but the end result is my desired response. So the PI control, again, based on the classic second order design, that's, if you look at our courseware, that's supplied with, that goes through all this. And so you get based on your peak time and overshoot specs, you find the natural frequency and the damping ratio of your prototype second order function, you find your PI gains. So if you go through the math, you can find that the closed loop rotor equation is as follows, quite standard, and your second order prototype system is as follows. But note that the rotor system matches the second order system, right? We don't have so that is only possible if you feed back the proportional gain directly. If you didn't do that, you would wind up with a 0 in the numerator in your rotor equation, and you would get more overshoot. So it would not match as well. So we go back to our live script, and what we can do is use the TF data command from the control system toolbox to obtain the numerator and denominator and get the DC gain and the time constant of our identified rotor model. And then we just enter the equations there and find the PI gains. So now the first thing I'm going to do is run a MATLAB simulation. So I want to run a quick MATLAB simulation by first creating the closed loop transfer function, right? So I don't need to do this by hand. I use, again, the control systems toolbox. So I'm using the DOF PI control command from MATLAB here, right? Again, because I'm feeding back the proportional term directly, I need to do the DOF PID controller command, because I have a slightly different paradigm. So I use that, and I use the connect block to create my closed loop transfer function. Then I run the step command, and that generates my step. Nice and easy. Just a couple of commands, and then I can see if my control design is correct. This is a command I've been using a lot, step info. So step info of that closed loop transfer function gives me the settling time, overshoot, all that stuff automatically, right? So I've been using this command a lot lately, and it's very handy. It's quite the time saver. You can see that the overshoot is 2.5% and the peak time is 0.15. That's exactly my design constraint. So great. So that's telling me that my PI design is correct. So I'm happy with that. However, if you look at the step response, it's giving a it's giving a reference of 1. That's 1 rad per second. That's minuscule. If you remember when we were doing the model validation experiment, that rotor speed was going about 540 rads per second, almost, right? And so when we're applying a 24-volt signal, which we need to do in order to get a good response from our pitch, you're looking at a much higher set point. So that's what we need to do, right? So that's why we go to Simulink now and have a more realistic simulation. So we're going to simulate the PI response with a 500 rad per second command. Okay, that's the first thing. So that's a major difference. It's 500, it's a set point of 500 times larger than the step command. We also have the actuator limits. We cannot forget that. We can't go more than 24 volts, right? That's our actual system constraint. We need to simulate that before implementing it to make sure that, to see how our simulation will fare with these new specs. So, so when we run the simulation, again, I'm logging the data in these two Simulink scopes and plotting it in a MATLAB figure. Now you can see now that it's getting saturated now with a 500 command, 500 rad per second rotor set point. It is saturating at 24 volts for about 0.2 seconds, right? And if we run the step info on the log data, which you can do, right? Step info you can use on a closed loop transfer function or on any data you have measured from a simulation or measured, we get an overshoot of 6.2% and a peak time of 0.2. So happy with the peak time. Overshoot is a little bit more than I wanted. I had my mindset at a 5% overshoot. However, given that this is just the first portion, I want to see how this will affect the ultimate goal, which is controlling the pitch, right? Because we still have a couple of steps in the control design process. And this can be iterative. I know I can always go back to my design, and if necessary, I can tune this to get a better response. But so this is okay. We can now move on to the second portion and how this lines up. So why is that? Why did the overshoot and the peak time increase? It's because of the actuator limit, right? We're dealing with that 24 volt limit, and that is one of the main constraints and challenges we have in this control design. We need to work with that. Okay, so rotor PI control is done. Now we can move on to the PID control. So the PID control, again, it's not quite your standard PID because we are feeding back the derivative directly, right? So this is basically a PI controller with rate feedback, is the proper terminology of this. And when we're simulating this in MATLAB and doing the design, we're assuming that there's no rotor dynamics, right? So assuming no rotor dynamics, basically like effectively you have a perfect rotor speed control. That is how we're doing the control design simulation. Now, if you recall from the system ID, we found that it was a second order transfer function, right? So we identified that second order model of the pitch. And one more note, I just want to mention, note that the control variable of PID is the rate, right? So we're feeding the rotor speed and not the voltage, right? So the rotor speed is going to be our control command. So anyway, the transfer function of the pitch relative to the speed of the rotor is a second order. And if we input the PID controller, we have defined the block diagram, we end up with a third order system. Now we need to match that prototype third order system to the prototype system, right? Which is like that. So you have basically it's a second order system with an additional pole, and you end up with this this third order numerator, right? So it's a step up from your standard second order design where you have a lot more terms now you have to deal with. However, this is but we don't need to do this tedious calculation on our own. We can leverage the Symbolic Math Toolbox. So basically, after defining your symbols, you define your plant transfer function and your control transfer function like I did on the previous slide. So, and you bundle that up inside a variable called TF equations. So you have the Y output pitch with respect to the input, which is the rotor speed, and then you have the PID controller. Then you can use the solve command. So you solve for the pitch, and it gives you the closed loop transfer function, right? So that alleviates, again, the tedious calculations, but also doing this is, it's prone to doing mistakes, right? It's because it's it's quite a nasty calculation. So, this is, again, a huge time saver. Now let's look at this a bit more closely, right? Because now you will see that the closed loop system we have for the AERO using the PID, even using the rate feedback, it doesn't quite match the prototype third order system, because you got that 0 in the numerator. Okay, this is going to affect our response as well, right? Because now whatever design we have, when it's an approximation of the actual system. So that is, but we need, and that's why we need proper simulations to see how that will affect our system. So the third order design specs for a controller will be as follows. We're looking at, we're going to design for a percent overshoot of 5%, a sudden time of 1.5 seconds, and then the extra pole will set at 2.5. The extra pole you can move around, right? So you can move to 1, 5, 2, 3, and like you need to do that because it's iterative. You're not too sure where the dominant pole should be. So that's why you simulate everything prior and then you look at, what is your control effort, and how does that affect your response, right? So that you can tune. And our desired response, what we ideally want, is a percentage overshoot of less than 10% and a cycling time of less than or equal to 3.5 seconds. So I guess you could say that we need to over design in order to compensate for the different approximations we have here and the different limitations. So once again, first let's use let's run it through a MATLAB simulation. So we create the closed loop transfer function using the DOF PID controller MATLAB command. We connect that, and then we run the step. So we run the step and we get a certain response. And if we run the step info, the settling time is not bad. So using the step info again, we're looking at a settling time of 2 seconds, which is more than a design constraint, but well under our expected 3.5 second settling time. The overshoot is quite large. So 13.1% is larger than 5% and larger than the 10% I want it to be. But let's see, but this is, again, it's an ideal simulation, right? So I don't want to stop here. I want to go in the Simulink and see how the Simulink behaves first before going back and designing this, because in doing this, right, it's always an iterative process. You look at MATLAB simulation a couple of times, and then you move on to Simulink, and then you can go back and forth, right, until you're happy with your results. So why is there such a large overshoot and the settling time is different? It's because of that third order approximation, right? It's that 0 in the numerator that's causing this this change. Okay, so now we run it with a more representative model. So this is the full Simulink simulation. So we're doing the full cascade control and trying to replicate what is going to happen on the actual hardware as close as possible. So here's the identified pitch and the identified rotor models we have, right? So we have both models now in the loop. We have the actuator limit, we have the inner rotor control that we design, and we have the outer pitch control that we design. And then we're applying a command that we want to actually apply, which is 0.3. So it's like 15, 20 degrees. That is our desired set point, right? So it's not 1 rad per 1 rad, it's 0.3 rads. So if we're using the logging capabilities of the Simulink scopes to log all of those, and we plot that in a MATLAB figure. And this is the response here. And if we use a step info on the log data, then we're looking at an overshoot of 12.2 and a settling time of 3.15 seconds. So actually the overshoot decreased a bit from 13 to 12. So it still exceeds slightly my 10% goal, but still, it's interesting that that decreased, right? And most likely because of the actuator saturation or something like that, or maybe the selecting time is good. It's 3.15, which is less than what my objective of 3.5 second. So like I said, the spec change is likely due to the 24-volt limit, but also it could be because of the inner rotor control as well, right? That introduces the rotor dynamics, which will change the response slightly. So now, given this, I can go ahead. Like those results are pretty decent. So first, and the control design there, I validated pretty thoroughly. I mean, it doesn't quite match my specs, but it's good enough to implement on the hardware and see how that will, how that fares up on the hardware, because that's the goal, right, guys? I mean, ideally, I want all this control design is to get a certain response on my hardware. So I want to see how it's going to fare up there before having to redesign all the time in simulation, because I know from it, based on experience, that the hardware is always going to have slight differences from the simulation. So the controller, as you can see, the Simulink model that we're using to implement this Cascade controller is very similar to the simulation one. So we have the inner rotor control, the PI controller. We have the pitch controller there. So again, we have the PID controller on the outer loop. We're reading the pitch angle and the rotor speed from the Hiller-Reid time base, and we're applying the voltage to the rotor using Hiller-Wright analog. So these are using the Cork target blocks. Here is a system in action. So I'm running the Cork controller now and applying the pitch. So the scope on the left is the voltage, the one in the middle is the rotor speed, and the one on the right is the pitch angle. So that was the response that that we got when I ran this a couple of days ago. So here's basically a snapshot of those responses. So you can see the pitch angle, the rotor. So note that the rotor, the yellow is your command and the blue is your measured, right? So you can see here, this is different than the simulation. The rotor is definitely different, and the voltage here. So the voltage is being saturated a bit. Again, we're logging all this data and plotting it in a MATLAB figure. So here you can see a little bit better. They're all stacked up. So we're getting some saturation here, which was expected. And you can see that the set point is in blue. So that is the blue is the commanded rotor rate from the outer PID controller. And then the red is your measured. So you can see it's not quite tracking. And then you have the pitch. But if we run step info, so again, I'm using that handy step info on the log data, we get a percentage overshoot much less than our full simulation. We're getting 6.4, and we're getting a settling time of 3.53, which is pretty much at 3.5 seconds, which was my expected, my desired, my ultimate goal. So, yeah, so I mean, so that is an example of a complete kind of iterative control design that I've done. So the results here, they're pretty similar to the simulation, and they satisfy my ultimate goal. I mean, not quite, so I could then go back and fine tune that and get that. But here's basically a summary of everything. So we had the ideal MATLAB simulation, selling time of 2, but that did not have any. That was a simplified simulation and had big overshoot. But when I simulated that in the full Simulink, I saw that there was an expected increase in settling time, but then the overshoot decreased a bit. And then we implemented it in the hardware. We had an additional settling time, right? So it added a bit more settling time and the percentage overshoot. So why is there a discrepancy here with the hardware response between the full Simulink, right? No surprise here, actuator saturation from 0 to 24 volts is definitely one of the main things. The other one is the rotor PI speed control. The tracking, like I indicated earlier, was not perfect, right? It's not tracking that set point perfectly. So that means that your PID controller will not behave as ideally. Now, that probably helped us with the overshoot. It probably decreased the overshoot. So there's a bit of a silver lining with that, right? It helped us in terms of the overshoot, but that's what probably added more to the settling time than expected from the full simulation. The other one's a third order PID design approximation, right? We have that 0 on top. That is not really what we're designing for. Another note that I didn't mention is the PID controller is not using a direct derivative like in the simulations. The actual implementation uses a filter. So the filtering can slow down the response. The sensor noise, that's what you need the filtering for, and that's what affects the, that's what makes it difficult to sometimes track that rotor speed, right? Because you do have a little bit of noise that's expected with even though it's a digital tachymeter, you get a bit of that. Finally, there's always going to be some unmodeled dynamics. So even though that the system identification was very accurate, that was a linear model, there might still be some unmodeled dynamics there that come into play, but I wouldn't say that's a major factor. The top ones are the main ones. So how could we improve it? We could go and assess the performance limitations and design the gains that way. Design our design constraints that way. We could try doing the anti-windup for the inner PI control loop. Maybe even try including a feed forward, which will decrease the amount of effort that the integral does to minimize the windup, minimize the dependency on the integrator term. You could use more advanced techniques, right? So you could get the state space model, develop LQR or pole placement, maybe a non-linear controller. Adaptive controller can be quite efficient with the actuators, the control effort. So that might be an interesting method to use. So there's a lot. And the beauty about Quark is everything is open architecture in our system. So you can definitely design all these, and many people have already. So what are the takeaways? Symbolic Math Toolbox saved us a lot of effort and tedious calculations, and it's easy to use. Step info, again, it's a huge time saver, and step info has been around for a long time. I feel people don't use it that much. So yeah, so check out step info. The Quark real-time control software is very well integrated within Simulink and easy to get all your measurements and implement your controller. The control systems toolbox, we use PID tool and closed loop transfer function step to simulate everything easily. And this is all done through the MATLAB Live script, where you can document and model your system and control design equations using LaTeX equations, add figures, all that stuff. So your whole design is nicely laid out in the Live script. And that's about it, guys. I think I ran a little long there. I apologize, but any questions for me?
Awesome. Thank you very much, Mitch. To the audience, please, if you do have any questions, this is the time to ask them. Please use the questions pane in the go-to control panel to send your questions over. Let me just see what's come in. One of the attendees is asking, when you designed the Cascade control, did you make sure the inner loop is faster than the outer loop? If yes, how did you deal with the slow dynamics introduced by the integral action?
That's a good question. The rotor, yeah, definitely the inner controller was a lot faster internally because the pitch position is fairly slow. So the inner loop was quite fast. And sorry, Armin, the question was the integrator windup, was it?
Sorry, so the question is, when you designed the Cascade controller, did you make sure the inner loop is running faster than the outer loop?
Yeah, definitely.
Yeah, okay. And if yes, how did you deal with the slow dynamics introduced by the integral action? I guess that's
Well,
that
the
was.
integral action, because the integral action, because I'm feeding it directly, it didn't really cause any slowdown because I got the response I had that was pretty fast. At at 0.2 peak time, that like based on it matched like my expected response of 0.2 seconds. So that was pretty good. 0.2 seconds peak time for the rotor, and the settling time is not, it settles very quickly. So I knew that rotor was, going very, very fast compared to the settling time of my pitch was, 3.5 seconds. That's kind of the settling time you're looking at, maybe a peak time of 3. So it's an order of magnitude larger than the inner control loop. So the integrator, no, I wasn't too worried about that. But having said that, maybe using a wind-up technique would have helped a little bit. Try to, lower that peak time a little bit and get a bit of a tighter control.
Thank you, Mitch. I know you commented on this in your presentation earlier, but can you please talk about again what type of an input you use for the initial identification purposes?
Okay, yeah. So when I ran the Simulink model, what I got is I measured the rotor speed and I measured the pitch angle and I applied the voltage to it. So that is the data I use in System ID. So when I identified the rotor model, my input was the voltage to the motor and my output was the measured speed of the rotor. So that was for the rotor transfer function. For the pitch angle, my input was the speed of the rotor and the output was the pitch angle, because the rotor model is with respect to the angular rate of the rotor. So those are the two sets of data I use to identify each of the transfer functions.
Great. Another attendee is saying interesting presentation. Thank you. Can you please tell us a little bit more about Quark and how do we configure it and what are its limitations?
If you want to get to know Quark, and you already have MATLAB Simulink and the required toolboxes, I would recommend you get a 30-day trial and try it out on your own. That'd be the best way to get exposed to the software, but in the meantime, you can also check out the web page we have, the Quark real-time control software on the Quanser website. Has a lot of information there, including the full documentation is available all online, so you don't even need to install anything. So I would recommend that. Limitations for Quark. Quark is very underused, so it has a lot more than most people know about. But for one thing, the limitations are if there's a toolbox, a certain advanced toolbox, or third-order devices that don't support the MATLAB and Simulink coder, i.e. you can't generate real-time code, then we can't use Quark with that. That would be like one limitation off the top of my head.
What sampling rate we're using for the experiments?
500 hertz for all of them.
Okay.
Which is more than enough, right? I mean, you could run it at 1 hertz if I wanted to, but I mean, given the time constants you're dealing with a mechanical system, 500 hertz is good enough. I don't think you'd see any improvements at 1 kilohertz.
Another attendee is saying, brilliant and informative presentation, thank you. And they're wondering if the same can be done with LabVIEW and a MyRio kit. And I assume an AERO if they have one.
Yeah, you could. You could. have used the NI LabVIEW system identification a long time ago on another system that was very similar, but it was basically a very similar system, but it was on a benchtop. And yeah, you could definitely do that. Yeah, but you would need the QFlex to my AERO panel with the Quanser AERO. So if you have that and you're already you have everything working with the standard VIs that we have for the Quanser AERO My AERO version, you could easily extend that to doing the similar treatment for sure.
And last question, Mitch, let me see if I could read this correctly. So the attendee is saying that the step info returns 2% settling time. And this person noticed that the value of the settling time were smaller than those returned by the step info. Did you use the 5% settling time, I suppose, in your calculation?
I think I used 4% settling time in my calculation. And yeah, you're right there, actually. Yeah, you know what? My bad. I should look at that again. But 4% settling time, 2% settling time. I'm not quite convinced that'll make a huge difference, but that is true. Thanks for pointing that out. I will update my live script and stuff. So thanks.
All right. I think that's all the time we have for questions. Once again, thank you, Mitch. This was fantastic, and a big thanks to everyone who joined us live this morning. If you do have any questions about this presentation for Mitch, please just reply to the last email that you received from us, and we'll make sure that it gets to Mitch, and he'll be more than happy to respond. To learn more about our products and services on how they can enhance your engineering labs, please visit our website at www.quanser.com and follow us, please, on social media, including LinkedIn and Facebook. And Mitch mentioned QLabs. Please note that we do offer a 2-week free trial of QLabs, and essentially that gives you access to the digital twin of many of our physical products. So you can run many of their experiments that we have on your PC without requiring the actual hardware. So just head over to our website to register for the free trial. Have a wonderful day and happy holidays, and hope to see you guys in the new year.